They're all very similar. And so you can see here that this column is titled the payment. And in the one that we did, the STEM problem up here, we had a $3,000 payment, and that's why negative 3,000 is there. But all of the other variables that you see here are defined in this way right here. So you can see if the interest rate is 0.08, then I% would be 8. And then if your goal in the future is to have $1 million, then the future value is $1 million. And this whole problem is about, you know, how long will it take you to have a nest egg of $1 million? Because you figure you need $1 million when you retire so that you can pay yourself what you want for your the rest, you know, for your retirement life. And so all of these are the same, and so most of the variables in the TVM solver that we enter are the same. So the STEM problem would be, and I'll just leave the first one blank because it's going to ask you, you know, how many years. And since we're there's no mention of a monthly payment or a quarterly payment, or even that the interest is compounded more, then payment per year is just going to be, and compounding per year is just 1. And so since n is equal to m times t, since the m value is 1, in this case, the n is going to equal the number of years. All right, so 8, we start with nothing, so the present value is 0. And in all of our present or all of our future value problems, the present value is 0. The payment is 3,000 if we want to get this one. And we're trying to calculate, we're trying to achieve $1 million. So $3,000 per year. How long will it take us to achieve $1 million? But we're getting a nice interest rate, so you can't just divide $1 million by 3,000 and, you know, do the number of years that way. Interest is going to really shorten that term. So we go up to n and calculate, and that's where you get this 43. And this means because payments per year, compounding per year is 1, this really does mean the years in this case. So it's going to be 43 years. Now, if you wanted to do one of these other ones, we first just, you know, for example, 6,000, you just come down and change the payment to, or 600 to 600. And go back up and recalculate the n. Now, we know that this answer is going to be much longer. If it takes 3,000 a year to amass $1 million in 43 years, if you actually invest less than that, like $600, and then calculate, you can see it's going to take you 63 years. So let's see. So this one would be, I'll just write it down and then I'll round it so you can see the whole. All right, so maybe we want to say here about, you know, certainly it's more than 63.5 years, but we're making one payment a year. So if you want to amass $1 million, if you only make 63 years worth of payments, you'll be just under the $1 million. So we need to make about 64 payments, yearly payments. So this whole problem, and you can see if you wanted to do this one here that we did in class, you would just change the payment amount to 12,000 and then go back up and recalculate. Yes, and that's where you get the 26.5. So I probably should round that one up to 27. So change the payment, recalculate the number of years. Change the payment, recalculate the number of years. And the TVM solver allows you to, you know, generate this table pretty quickly. Change one number, recalculate something, change another number. Over in this column here, now we're keeping the payment fixed at 3,000. So in every one of these examples, we want to know how long it's going to take payments of $3,000 per year to, we're looking, how many years is it going to take, find T, if we make $3,000 payments per year at these various interest rates. And so in this table, the I% is what's changing. So those bottom numbers are okay. and the interest rate is what's going to change. So in the first one, the interest rate is 1%. So the R value is 0.01, 1%, and then the I percent is 1. Now, it's going to take a lot longer to amass $1 million if you have this real small interest rate. This is almost the same as putting your money in the mattress where you earn 0% interest. All right, but everything is set there. So alpha, enter, and this one would take, you eventually would get there, but you'd have to save for 147 years, and nobody's going to be around that long. So 147 years would not quite do it, so we probably want to go up to the next year. And so for this one, you just change the I percent in the next row to 5, and then go up and recalculate the years, 58. Go down, change it to 8, and recalculate the years. And then this last one down here, we're getting a 20% interest rate. So with a 20% interest rate, it's only going to take about 23 years. Does that help, Brendan? Now, once you get all these numbers down here, it asks you to reflect on what you've just observed. So does the payment, so this one would refer to the evidence that you see in the first table. Does the payment have a significant impact on the number of years that it would take to reach $1 million? And so just refer to the evidence up here in the table. You know, yes, as the payment goes up, the number of years goes down dramatically. And then for the second one, does the annual interest rate have a significant impact on the number of years? So then for the second one, you're going to reflect on this table here, and you're going to say, well, when the interest rate goes up, look at how many years it takes to achieve millionaire status. It goes down, down, down. So in a couple of sentences, describe what you see in the tables. Okay, so I thought what we would do then is I would just maybe work through these and just to kind of give you a sense of the variety of problems that you will see, the variety of applications. All of them are applications, and maybe give you some things to look at, to consider as you're doing these problems. We do have the Tvm Solver, but it can't be used for every problem. So you need to know the ones it can be used for and the ones that it cannot be used for. Generally, the ones that it cannot be used for are the ones that involve the effective annual yield, the effective rate. So number one, the Tvm Solver is not going to be useful. And then anything that talks about simple interest would not be appropriate. Right. So you'll definitely see something on simple interest too. I don't know if it's on this particular sample exam or not. Okay, find the effective rate to the nearest 100th% corresponding to a nominal rate, and that's a value of R. That if we're going to use the formula, 0.0499, where the interest is compounded weekly. Now, we don't use the M to be 52 very often, but in this case it is. So the M value can be any one of our popular values: 1 for annually, 4 for quarterly, 12 for monthly, 52 for weekly, 2 for semi-annually, and 365 for daily. But you know, you go to that formula, and I think I may have even included the finance formulas here. But on your formula sheet, it's clearly labeled. You know, and periodically you might want to just read this formula sheet. You know, plan to read this formula sheet 3 or 4 times during your taking the test, because it might signal something to you, like effective annual yield is this guy. One of the things we haven't done, I don't think I put on there, is the discounted loan. So that formula sheet I just showed you was an old one. But here's the formula. I don't know if we use Y or R effective, but the formula is we're just going to take 1 plus R divided by M to the nth power. We're assuming that T is equal to 1. That's why there's no T there, and the present value is equal to 1 as well. and then we're going to subtract 1. So the hardest part is recognizing that it's an effective annual yield problem and that you must use this formula. When we do use the formula, we must use the decimal version of the percent. And all of this can be entered into your calculator in one line. Now, the effective annual yield is like a simple interest rate for the year. So you need to report your answer as we would a normal interest rate, that is, as a percent. So you're going to see on the calculator the decimal version. So there's the calculator display, and be sure to circle your answer. Okay, here's something that's very important with the TVM solver or anything that you have. You must indicate your answer somehow off to the side. So if you just leave the inputs of the TVM solver there, then you're not really taking that last step and then concluding and identifying what the answer is. So that is, you must go one step further than this and say 5.1 hundredth of a percent. Here's the percent, tenths, hundredths, one more place, and then circle the answer in the correct version. Now, did I show you this calculator function that says like a little arrow and then it's convert to effective? Did I show you this? Can't remember. There is a calculator function that looks like this, and that arrow means convert to, so convert to effective. And the two numbers that it needs are I% and M. And that's because those are the two variables that are used in this formula. So if we give the calculator those two values and signal that we're going to use the effective annual yield formula, then we can also calculate the effective annual yield. And it would look like this for our problem. Now remember that for the calculator language, we don't enter in the decimal, but rather we enter in the percent. So 4.99 and then comma, and then you've got to give the M factor. And that function right there is in the finance menu. So you need to go to apps, finance, number 1. All right. But when you go there, you don't want to go into the TVM solver because that's not what we're after. Turns out that there's a lot of other functions below number 7 there. So if you just scroll down, you'll see the one we're after. And it's option C. So I'm going to put enter here. And then that's what you see. So now we just have to enter in our two values, 4.99 and then a comma and then 5.2. The comma is right above the number 7, if you've never used that, comma. So I'm going to hit enter here and then just compare what you see on the screen to our answer. And you can see if you round it to the nearest hundredth of a percent, it's the same value. So using the formula, there's the number. Using the calculator function, there's the number. Notice that those are correct to 10 decimal places or whatever. Okay, next one. It's probably a good idea to read this a couple of times, and along the way, there'll be some numbers that you'll know, oh, that's got to be the I, or oh, that's got to be the T. But there are others that it's unclear, like a dollar amount. Is that going to be the payment? Is that going to be the present value? Is that going to be the future value? So Becca has accumulated $7,500 in a savings over a several-year period. She plans to invest her savings in an account earning 4%. Estimate how much she will have in the account after 54 years. Wow, that's a long time. Using, I'll just get rid of rule of 72. Now the rule of 72 says something like this. It says that a time that it takes your money to double is equal to 72, that's where the rule, divided by, that's where the rule comes from, the interest rate. So if you take if you take 4%, which is the interest rate, and you take 72 divided by 4, that's equal to 18. And that means that at a 4% interest rate, your money will double after 4 years. With a 4% interest rate, your money will double after 18 years. Then it'll double again after the next 18 years. And then it'll double again after the next 18 years. And notice I just contrived a number there so that it matches perfectly. So at the beginning, you have $7,500. After 18 years at 4%, that money is going to double. So that money after 18 years goes to 15,000. After the next 18 years, it doubles again, but it doubles from the 15,000. So it's going up to 30,000. And then in the last 18 years, it doubles again. So from 30,000 to 60,000. So what we're saying here is that we think, as an estimate, we're going to have $60,000 in that account. Okay. So let's put everything, the present value, which is P in our formula, is 7,500. And if we use the TVM solver here, we're going to have to put in negative 7,500. If you use the formula, of course, you're going to put the positive value in there. The I% is equal to 4. Interest rate is 4. The T, number of years, is 54. And you can see 4% per year. As you read over the rest of this problem, I don't think there's any mention of a compounding factor other than just per year, which means once per year. So the M value is equal to 1. Put those two together and you get the N value, 54 times 1. Payments per year, compounding per year is equal to 1. In this case, as we think about the problem, there's just a lump sum at the beginning. And so that's another big decision you have to make. Is this problem dealing with a regular payment? We call that an annuity. Either you're making a regular investment while you're making a regular monthly payment. Anything where the payment comes back over and over and over again periodically, every month, every quarter, every week, whatever, and it would be an annuity. If there's no mention of a payment, then the payment is 0. Okay, and what we would be calculating here is the future value. So this is one where you have a choice where you can use the formula or the TVM solver. And for this one, the formula probably is just as easy as the TVM solver. So I'll use the formula here. And then you can use the TVM solver if you like. We know the future value is going to be close to 60,000 because of this analysis we did over here on the side. But let's check it out. 7,500 and then 1 plus the interest rate. When we use the formula, the interest rate has to be the decimal version of the percent. And then the M value is 1. And then we have to the 1 times T. All right, so I'll just plug that in on the home screen of the calculator. 1.04 to the 54. Okay, how close to 60,000 is it? 62,000. But at least we're in the ballpark. And if you go to the TVM solver, and by the way, this is instructive. I mean, for these problems, if you're good with the formula, do it in both ways. That's the way you confirm your answers are correct. 54 for N. At an interest rate of 4, we start with 7,500. It's cash out, so it's a negative. We're not making a payment. Payments per year, compounding per year is 1. And then there it is. And it's the same exact number. It has to be. Uses the same formula. If you use the TVM solver, and you'll use the TVM solver in many of these problems, sometimes multiple times, I'm going to ask you to tell me what each of the inputs are. So the work for the problem, and you can see it, the kind of work that I expect, in the solution of this sample exam, where it lists all the TVM solver and what you typed in. This is the only way that I can give you partial credit. So if you don't have any of this information down and you're off by, you know, $7, it's like, gee, they probably did everything correctly, but, or a lot of it correctly, but ended up with the wrong answer and there's no supporting work. So I can't give any partial credit at all. They're all slightly different. Okay, now we have Kelsey and Eric's home, right? So we do have a couple of contexts that involve home purchases, mortgages, refinancing, all those other things. It's currently appraised at $183,500, and suppose that it'll appreciate in value at a rate of this amount per year over the next 10 years. What will the home be worth in 10 years? So this problem is almost identical to the earlier one, to the previous one. And we just don't know what the value is. You know, it's not like we're taking out a loan on the home here. It just tells us that it increases at this small rate. It's not losing money, 0.79% per year. All right, so here would be the work that I would expect for the TVM solver. If this is a kind of a 3-point problem, then you get 1 point for the answer. So if you write only the answer and it's correct, you're going to feel like there's been some injustice done because you'll receive 1 out of 3 points for a correct answer. The rest of it is displaying your work, so please do that. 10 years, this is another one where there's no mention of compounding. I% is this number here. Now, if you use a rate here and you use the formula, you're going to have to put 0.0079 in for the R value. For the I%, 0.79. We start off with the current value of the home. There is no payment. This is not an annuity problem. There's no payment, no investment, no regular amount of cash outflow. The future value is what we're trying to find. And we're just compounding 1 time per year. It's kind of a silly problem if you want to know what your house is worth, assuming an interest rate, and you do compound interest. And we could do compound interest, but you can see it's not going to change the value much. All right. So plugging all the numbers in, 10.79. All right, there we are. The preliminary inputs ready to go. And then solve, and there it is. So your $183,000 home grows in value over 10 years, about, what would that be, about $15,000 appreciated. And when you sell it, you get to take advantage of that appreciation. All right, so this number is 19852.86. Okay, now let me just explain how I'm going to grade this. If this is all you give me, this right here, you've shown all the work to get the correct answer, but you have not identified the correct answer. So if this problem was worth 3 points, you would get 2 of the 3 points because all of the work is correct. To get the 3rd point, you have to tell me what the answer is. You can't infer that I'm going to read your answer from the table. So it should be rounded to the nearest penny, the $ included, and kind of off to the side somewhere. All right, the next one, this is a great problem for the TVM solver, so I'll let you do this one while I work it out via formula. Let's see if I can beat you to the end. Okay, how many years would it take to pay off a credit card that has a balance of $7,491? If the annual percentage rate on the card is this number, and the monthly payment is -126, and the interest is compounded monthly. And then there's a second part of this one is, there should be a question there, is how much interest of all that money that you've paid back, how much of it was interest? All right, so this one, we're going to be using the formula that the present value is equal to the payment times 1 minus 1 plus r over m to the negative mt all over r over m. So this really is an algebraic nightmare. So you should be thankful that you're not required to solve a problem in this way. I'm going to divide both sides by 126, and then I'm going to multiply both sides by 0.1995 over 12. So that will cancel, and these will cancel. And then times 0.1995 divided by 12. What a nightmare. 0.98839583333. Okay, equals. All right, now I have all of this. 1 minus this guy. I'm going to subtract 1 from both sides. Get rid of that 1. And then this number would be a negative, right? Negative 0.01160416667. And then over here, I got a negative 1.1995 over 12 to the negative 12t. I can multiply both sides by negative 1, and that would just make that, I'm not going to write another step for that. So both of those positive. And then I'm going to take the natural log of both sides. Now there is a property of logarithms that will enable me to take this exponent here out in front of the log and multiply it. So we have the natural log of 0.01160416667. Notice there's no rounding going on. Equals negative 12t times the natural log of 1 plus point, all this. All right, now to get t by itself, I have to divide both sides by the negative 12. I also have to divide both sides by the natural log of 1 plus 0.1995 over 12, so that those are gone. So that leaves me with t, and I'm going to plug all this into my calculator, and then we can compare answers. We have n is what we're looking for, so I'll skip that one, 19.95, just a huge interest rate, which is the case on most of these credit cards. Our present value is $74.91. The payment is negative 126. At the end, we'll have it all paid off. Monthly payments, and then alpha. So there it is. And then we divide that number, 22.52. All right, so the second question here says about how much interest would have been paid over that 22 years. And so I'm going to go back to months, and I'm going to say, well, if we made 270 payments, we'd still have a little bit left. So it's really going to take 271 payments in order to pay this off. And we're making payments of $126. So if I take the 271 payments of 126, that means that after 22 years, this is how much we paid. But the original loan was only this amount. So this is the principal. Everything else is interest. So there's just a huge amount of interest paid. And this is typically the case when you make only the minimum payment on a credit card. So it's just a subtraction. This is the total payments, or total paid, however you want to say it. And of that, part is principal and the other is interest. So if we take the total paid and subtract the principal, we get the interest. And so about over $26,000 in interest payments over the 22-year period. All right, so we're going to have actually two things circled here. One for the number of, or how long it would take. And, oh, it did say how many years. So you'd actually have to circle the years number and then the interest on this one, both of them. We don't have to do these in order. So if you'd like me to skip ahead and do one of the later problems, we can do that as well. I don't want to go too fast here and confuse you. But you know, these should all look familiar because you've done problems like this before. And I would consider all the problems on this page, just for your information, most of them are just one-step problems. Now, sometimes they'll ask you 2 questions in the problem, in which case they're 2 one-step problems, but generally it's just one application of the TVM solver. The problems that come later, you're going to have to think, but part of the problems will be more than one step. Quentin wants to save $60,000 for his son's first year of Harvard tuition in 14 years. 14 years, the tuition at Harvard is probably going to be $80,000 or more. How much money must he deposit at the end of each 6-month period in an account earning 6.95% compounded semi-annually, so that he will have enough to pay for the first year at Harvard? All right, how much money must he deposit at the end of each 6? So when you see that there's a suggestion here that regular payments are going to be made, then you know that this is an annuity. So you have to either use the present value annuity formula, where the payment is going to be non-zero, or you're going to use the future value. In this case, Quentin is taking out this money and he is investing it. This is called a sinking fund. And in the sinking fund, and this is one that students have difficulty with, and the choice is, do you let the present value be the 60,000, or do you let the future value be the 60,000? And it turns out in this case, you want the future value. You want him, he wants to save, and so that 14 years in the future, because of his savings and investing, he has 60,000. So this one, we would actually let the 60,000 be the future value. And since it's a future value problem, the present value is 0. How much must he deposit? They're asking for the regular investment amount, so that's the payment. We do know that T is equal to 12. And here it says, it gives you a clue as to what the compounding factor is at the end of each 6-month period. So at the end of 6 months, and then at the end of another 6 months, that gives you a year. So because of that, M is equal to 2. We are compounding interest semi-annually. But if that wasn't enough information, over here it says compounded semi-annually. So there's 2 different ways to confirm that the compounding factor is the same, and it is 2. So payments per year, compounding per year is equal to 2. So these payments are going to be made every 6 months. The interest is compounded semi-annually, and it is 6.95%. Okay. Many problems, but not all of them, will ask you to calculate the interest. We can also calculate the interest here. And how much money? So we have T is equal to, I don't know why I wrote 12 there. T is equal to 14, and M is equal to 2. So if you put those together, N is equal to 2 times 14, or 28. 28, interest rate, 6.95, payments. This is the investments every 6 months. That's what we're trying to find. Start with 0, and we want to get up to $60,000 in the future. Payments per year, compounding per year, 2. All right, so we have N is 28, and then future value 60, present value 0. Payment, we're going to go up to calculate. Payments per year, compounding per year, and we've got the right interest rate. Okay, so I'm just going to try to figure out what it is right now, or at least tell you some reasoning you can use. 2 payments being made, so that means 28 payments. So if you just take the total amount you want to have and divide by 28, there would be the payments if you weren't earning any interest, but you are earning interest, so you're probably not going to have to pay as much. So I'm looking at, this is a long period, this is 14 years. So, you know, maybe it's somewhere between $1,500 and $2,000 that you have to pay each one of those quarters. All right, but it's worth a kind of a consideration. Even lower than that, $1,300. And so we will write down the, and I'll do the interest calculation over here. If we make payments of 1301, or Quentin does, 09, and makes 28 of those, then Quentin invested a total of $36,000. $36,430, a little bit more. Every 6 months, he invested 1301.09, but this is the total amount invested. But remember, at the end of the 14 years, he actually has $60,000. So the difference between what he has after 14 years and what he actually put in himself is the interest. So we're just going to take that number and subtract it from 60,000, and that turns out to be 23,569.48. Again, that interest calculation is not a TVM solver problem. It's just a subtraction problem. And here's the formula. We usually do a subtraction problem because we usually solve this equation for interest. And if you subtracted the principal from both sides, you would get the total accumulated payments minus the principal. This formula is not going to appear on the formula sheet. It's just something that you know you need to do. And if you want to break that down even further, the total accumulated payments is equal to the regular payment. Whether I hesitate here to write monthly payment because it might not be monthly payments you're making, but it's the regular payment times the number of times the payment was made. Okay, again, I'll pause a little bit and ask if you have any questions or you'd like to go see one of the problems that are later on in this. I do that just because I don't think we're going to get through everything in the time that we have, but let's take a look at the next one. Chandra, an 18-year-old college student, deposits $600 at the end of each quarter. So this again is an annuity because the payment is going to occur multiple times, periodically, in this case, each quarter. So the M is equal to 4, which means payments per year, compounding periods per year, also 4. The payment is 600. Interest rate, 9.53, compounded quarterly. Good. Each quarter, quarterly, they have to match. How long will it take? Find N, or find T. For Chandra to accumulate her goal of $5 million. Will she likely reach her goal? All right, so in this one, it's the N that we're looking for. And remember that we're compounding quarterly. So when you do the calculation here, whatever N is, you have to divide it by 4 to find the number of years. So quarters. And that's because payments per year, compounding per year is 4. All right, I percent is 9.53, going right down the list. The present value in a future value problem is 0. The payments cash out, negative 600. Future value is what our target is, and that's the that's the 5 million. And then payments per year, compounding per year, that's the 4. All right, with those inputs in there, we can calculate the N using the TVM solver. And then we can answer their last question, which is it likely that Chandra is going to meet her goal? Start with nothing, make 600 payments, try to achieve $5 million quarterly. All right, check to make sure everything is in there correctly. All right, I think that's it. We'll do an alpha solve there, and we get 224.96 quarters. All right, so write that in there. 224.9261015 quarters. All right, so then if we want to divide by 4, then we would get the number of years. So I'm going to go and to the end and just say divided by 4, and that's 56 years. So yeah, Chandra could do it. I suppose she would, 56 years attached to her 18-year-old age. That means she would be, what, 74? So if she worked for 74 and continue to make those payments, she could become a $5 millionaire in her lifetime. All it takes is $600 a quarter, $2,400 a year with a nice interest rate. Okay, so this next one, you'll recognize it because it appeared, one like it, appeared on one of your finance worksheets. So I guess I would recommend here drawing the picture and breaking it down into the 2 steps. So Clayton is 25 at the beginning, and so here, age 25, and he wants to retire at age 60. He wishes to make monthly deposits in an account, all right, so that's over here, compounded monthly, so that when he retires at age 60, he can withdraw $1,000 a month for 25 years. Okay, so 25 years over here, he would be age 85. All right, so they give you enough clues to be able to break down the problem. 25 to 60, that's 35 years. So they don't tell you the T, but they do give you the clues that you can then use. So they give you the age clues, and then they give you the number of years in some case, and sometimes, like in this one, they give you a combination of those 2. All right, so my first reading of this problem just enabled me to write this chart. So now I'm going to go back and read again and fill in the details. Okay, he wishes to make monthly deposits. Okay, so M is equal to 12. That translates into payments per year, compounding per year. In an account paying 6.3%, so I percent is 6.3, compounded monthly, so that when he retires, he can withdraw. Okay, so now we're going into retirement, so that when he retires, he can have a payment equal to $1,000 a month for 25 years. And then how much should Clayton deposit here each month? What should the payment be here so that there'll be enough money over here? Now, it might seem at first glance that they didn't give you enough information for this problem. And the reason for that is that we're going to calculate the future value that Clayton has in the first 35 years, and then that becomes the present value, whatever this number is, it becomes the present value in the second part of the problem. And we're going to assume that the money stays in the same account, so therefore it's earning the same interest rate in the first 35 years as it is in the last 25 years. The second part of the problem is a present value problem, so the future value is going to be 0. The first part of the problem is a future value problem, so the present value is going to be 0. So I think we mentioned last time that chronologically, you know, the saving and investing occurs first, and then the annuity, the retirement annuity comes second. But when you actually do this problem, you have to first figure out, you know, how much you need to have at age 60 so that you can pay yourself $1,000. All right, so we're going to do this part of the problem first to calculate how much we need how much Clayton needs at age 60 in order to pay himself. All right, so payments per year, compounding per year is 12, and the number of years is 25. So there are going to be 300 monthly payments in that 25-year retirement over here. The interest rate is 6.3. Present value is 0. Present value is what we're going to calculate. The payment is negative 1,000. Future value is 0 in this problem. And the payments per year, compounding per year, would be 12. All right, how much do we have? All right, 25 years, $1,000 payments, that's 12,000 per year. 25 years, $300,000. So we know the payout's going to be $300,000, but we certainly don't have to have that amount here. Maybe just over 100,000 is all we need. Let's see. We come up here and calculate the present value. And we need 150,883.3952. So we only need 150,000 in order to pay ourselves $1,000 each month for the last 25 years, presumably that we're alive, planning on dying about age 85. All right, then the reason why it seems like we don't have enough information is because we're now going to take the amount that we do need at age 60, and that becomes what the future value of this annuity here is. So we're going to enter in 150,883, and we'll call it 0.40 if we do the rounding. And then this is a future value problem where we're trying to find out how much do we have to invest in order to pay ourselves $1,000 at the end of in our last 25 years of retirement. All right, so over here, this is 35 years of monthly payments. So N sometimes is the hardest one to figure out. In this case, it's 420, because if you think about making monthly payments over a 30 or 5-year period, that's how many payments you're going to make. That is the definition of N, the number of payments. 6.3, that didn't change. We start with 0 for future value problems. We want to calculate the payment, and we want to have at the end of those 35 years. All right, so the payment, and under $100. Okay, just so you know, these problems, they're hard, but because there's so much work, you know, if I give 3 points for a problem up here, then I basically have to double it down here. So write down as much as you know, write this grid, all of it counts as partial credit. But eventually, and when I'm grading like this, I'm going to look for this answer. If I see this answer right here, I'm just going to scan the work. I'm not going to read it. I'm going to scan it just to make sure that you did it, and then you get full credit. But if I see only this answer without the work, then you're going to lose most of the points, because I have no idea how you came up with this answer. So work is important because it tells me you're thinking. By the way, 98.79 times the number of times we made that payment, what was that, 420? This is how much that Clayton actually invested through this entire, you know, what was it, 35 and 25, 60-year period. This is how much he contributed. And he contributed it all in the first 35 years. $100 every month. Insignificant. But in the end, he's actually paying himself $1,000 over 25 years of monthly payments. So 25 times 12, 300 payments of $1,000. Compare how much he invested, how much he actually gets paid out. Quite a deal. Invest early, invest often. All right, let's go to the 3rd page and let's look at the home ownership. There's lots of problems, lots of different parts to this one, and many of them, but not all of them, use the Tvm Solver. Others just use arithmetic. So let's read on. You know, some of these home paying off problems, they say, well, there's a, this is what the home is valued at, but then they have to put 20% down. In this particular one, it basically goes right to the mortgage and say they took out this mortgage. And so their house may have been, 225,000, and they came up with a chunk of money as a down payment and then took out a loan of 188,000. But in this context, the present value is the amount of the loan. So that's going to be the 188,000. The interest rate, just take these in order as a percentage, 3.95. Interest is compounded monthly. And all of these home problems, mortgage problems, and the car monthly payments, they're all done in months. So payments per year, compounding per year, 12 monthly. After 5 years of paying off the original loan, they decide to refinance because the interest rates have dropped. They refinance the balance of their loan using a new 25-year mortgage. So after 5 years on their original loan, they would have 25 years. So they must have figured, well, let's just take out the same thing. So we're going to stay on track to pay off this house as originally scheduled. Okay, so you did these in the finance worksheet too. Similar, I guess it was one. So you did one, so you've already done that. And if you recall, for these refinance problems, there are 3 steps. You first have to calculate the monthly payment of the original loan, then figure out the present value after those 5 years, because in a refinance, you have to pay off the old loan after 5 years and then restart a new loan at a lower interest rate. And then the third step is to then calculate the new monthly payment. And then if there's more after that, how much are you going to save? So 3-step problem, and they actually take you through them here. So this is step 1 of the refinance problem. What is the original monthly payment? Step 2 is right next to it. What was the balance of the original loan after the first 5 years? All right, so we're going to calculate the present value here. Up here, we're going to calculate what the payment is. And then the next one is what is the new monthly payment? And that is step 3. So the 3 steps, these problems are kind of guiding you through the 3 steps. All right, and again here, it's the new monthly payment with the interest rate at the lower amount, which is the 2.875. Whereas up here, this is the interest rate of the original loan, which is 3.95. The present value, what students like to do sometimes is they like to insert this interest rate a little sooner than they should. This one is the present value on the current loan, where the interest rate is 3.95. All right, so in the original loan, it's a 30-year loan of monthly payments. So N is 360, 30-year loan. The original present value is the 188. Payments per year, compounding per year, 12. And this is a present value problem, so the future value is 0, and we're really interested in the payment. So we'll do the Tvm Solver to do this quickly. And maybe I'll just do all of these together just to show you that as you go from one step to the next, you change one number and recalculate something else. And then when you go to the next step, change one number and go to something else. All right, so here, N, after 5 years of monthly payments, that's 60 payments. 60 payments have been made. So that means that 300 payments remain. So the number for N, and this is another sticky point for students, that the N value is the number of payments that remain and not the number of payments that you made. Interest rate, present value is what we're after. The payment we're going to get from up here. And once again, future value is going to be 0. Payments per year, compounding per year, still talking about the original loan. All right, so we're going to take the payment that we calculate here and bring it down and insert it here. All right, and then the last one with the new monthly payment, the N is going to be 25 times 12, which is 300. New 25-year loan, new interest rate. The present value is what we find here, and then we bring it down. So you really can't answer the next problem until you do the previous one. Again, future value for a present value problem is 0. Payments per year, compounding per year, again 12 throughout. All right, go ahead. First one, we have 360 at the interest rate of 3.95. The present value of the loan is 188,000. And we calculate the payment, and you should get $892.13. Now I'm just going to leave that number in there. So when we do this problem, the second one, to determine the present value, what's changing is that we're now changing the N because we only have 300 payments remaining. So we change one number and then calculate something else. I'm going to change one number, that 300 or 360 to a 300, and then calculate the present value. Everything else is the same. So unfortunately, we still owe most everything. On a $188,000 loan, we still owe close to $170,000. There it is, 169,903.64. Yes. And then in the last problem, again, we change one number because, all right, I'm just reading it again because sometimes in these problems, you know, whatever it takes to refinance, you roll over those closing costs into the loan present value, but they didn't suggest that here. So I'm just going to now change the interest rate to the lower interest rate, 2.875, and then recalculate the payment. The present value is what we still owe, taking it out over 25 years. New payment, it goes down from about 900 to 800. So close to about $100 savings for each payment. And all you did was go fill out some paperwork at your local bank to refinance your loan. And immediately save $100 a month or $1,200 a year in your monthly payments and your living expenses. Still living in the same house, still have the same loan. All right, so this would be 794.70, let's say.